as announced here, the seismic analysis of the retaining structures and shallow foundation, which is to be delivered by Dr. Hasan Rangwala. And this webinar is being organized in the memory of uh, Professor M.D. Desai, who has served for 25 years in SV Regional College of Engineering and Technology, presently known as the SVNIT Surat. So in memory of the 9th anniversary of Professor M.D. Desai, we are organizing this webinar and lecture to be delivered by Dr. Hasan Rangwala. The introduction of the Dr. Hasan Rangwala will be given by our research scholar, uh, Nazim Ali Chinwala, who is very active member of the Indian Geotechnical Society, very experienced member. Nazim Chinwala is also executive committee member of Indian Geotechnical Society, Baroda chapter. He is working very actively for both the chapters, Vadodara and Surat. The most of the webinars which we are organizing here, it is with the help of the Nazim Ali Chinwala, most of the work which he is doing. So before giving the introduction of the Dr. Hasan Rangwala by Nazim Ali Chinwala, I request Engineer Hitesh Desai to say a few words about the Professor M.D. Desai.
Good morning, everybody. Welcome to this webinar. Now, this webinar is as a tribute on 9th death anniversary of Dr. M.D. Desai, who is our guru. Born on 30th April 1936, Dr. Desai was graduated from MS University and he has done his PhD from South Gujarat University, and his guide was Dr. Alam Singh. I think name of Dr. Alam Singh is known to every geotechnocrat. Dr. Desai is a very active member, was a very active member of Indian Geotechnical Society. He served this IGS for more than 40 years. And from the beginning, he is connected with Indian Geotechnical Society. And before his death of 45 days back, he attended the last IGC at Delhi. That is in December 12. So Dr. Desai, he has guided our Dr. Solanki, who has guided now more than 25 students, PhD students. So now we put the calculations that he was the guide of Dr. Chandresh Solanki. And he worked for IGS. Surat chapter was the first chapter in Gujarat. It is one of the oldest chapter in the Indian Geotechnical Society, and all credit goes to him. He organized 2 IGCs in Surat, and that is in 1982 and 1991. And he delivered Indian Geotechnical IGS lecture at IGC Madras or Chennai. So his knowledge was not only in one direction. He was very equal, competent. For even he has guided MTech thesis in concrete also, and he has the very good knowledge about the hydraulics also. So nowadays, what we see a multi-speciality hospital, it is something like that. That he was a multi-subject consultant for the South Gujarat University, South Gujarat area. About his enthusiasm, what say is, only 3-4 days before his death, he has signed the PhD thesis of Professor Pratima Patel at the hospital bed. So practically we can say that till the end of his life, he worked for geotechnical engineering. I think this is more than enough to know those who don't know or have no idea about Dr. M.D. Desai. And he was the guide to many of us, those who have brought up, as whatever is the knowledge we have at present, all the credit goes to Dr. M.D. Desai. Thank you very much. And we pay tribute on his 9th death anniversary. Thank you.
Thank you, Engineer Hitesh Desai. We have with us Dr. Vikas Patil and Sanjay Verma, our senior colleague of the IGS. I thank for your presence and take the note of your presence. I request Nazim Ali Chinwala to introduce Dr. Hasan Rangwala.
Okay, very good morning to one and all who are present for this webinar. Dr. Hasan M. Rangwala is an assistant professor at Civil Engineering Department at Nirma University since 2015. He obtained his BE degree in Civil Engineering from LD College of Engineering, Ahmedabad in 2008 and MTech degree in Earthquake Engineering with specialization in Soil Dynamics from IIT Roorkee in 2010. He completed his doctoral research and obtained PhD degree in 2014 from IIT Roorkee. His doctoral research area was earthquake resistance design of foundation. He has an academic experience of 1.5 years at MANIT Bhopal prior to joining at Nirma University. Dr. Rangwala has 2 book chapters, 4 international journal papers, and 6 international conference papers to his credit. He is actively involved in supervising major projects of MTech CASAD as well as various students project at both undergraduate and postgraduate level. Dr. Rangwala has completed 2 research projects funded by Nirma University. Currently, he is involved with a research project funded by Nirma University. He is actively involved in testing and consultancy work related to soil investigation, foundation design, etc. He is teaching subjects like geology and geotechnical engineering, foundation engineering, reinforcement sustainable building technologies at undergraduate level and foundation engineering at postgraduate level. Dr. Rangwala is recognized PhD supervisor and currently supervising 1 PhD student. His area of research include analysis and design of foundation and retaining structure, dynamic properties of soil and reinforced earth. So with this short biodata, I welcome Dr. Hasan Rangwala sir to deliver his webinar lecture on the topic of seismic analysis of retaining structures and shallow foundation.
Thank you. Thank you very much, Nazim. Thank you very much, Solanki sir, for inviting me for this particular lecture. And first and foremost, I think I would pay my tribute also to Dr. M.D. Desai on his death anniversary today. So thank you very much to the SVNIT student chapter of IGS as well as the IGS student chapter. With that, I think I would start with my presentation. Just share the presentation.
Okay, thank you, Dr. Hasan Rangwala. Before starting your lecture, we welcome Raghuveer Rao here for your presence here in this webinar. Thank you, Raghuveer Raoji. Thank you.
I hope my presentation is visible to you.
Yes, it is
Yes.
visible.
Okay, thank you very much, sir. So basically, the topic of the talk is seismic analysis of retaining structures and foundation. The topic came out as we have discussed about getting a session on the basis of some of the works that I have done in as research scholar at IIT Roorkee, where I have basically conducted my research in seismic analysis of shallow foundation. And as most of our eminent participants knows that whenever we are talking about shallow foundation, we need to have earth pressures, and then on the retaining structures knowledge should be there. So that is how I came to this particular thing with the help of some of the work conducted by me at that level, as well as a few literature review. So if I just go through the content, that is basically I would be conducting or I will be talking about a few literatures that has been there on retaining structures as well as shallow foundation in very brief, and a few things that I have done at my PhD during my PhD work. So with that, I would just like to start with basically we are talking about the seismic forces or the earthquake forces. Okay, so what happens to the soil when there is an earthquake is during an earthquake I would have a wave propagation, right? So in the wave propagation, the soil media would have earthquake acceleration or known as seismic acceleration, and this causes the inertial stresses in the soil mass. Okay, and this inertial stresses has to be taken further in the analysis while conducting the seismic analysis. So that is the basic concept or say conceptual thing. While we will go from static to seismic analysis just for the review of the seismic analysis as we start. So first, I would have just divided the presentation in seismic analysis of retaining structure and seismic analysis of foundations, and based on which both I would have some discussions on say the thing literature available in the available with us. Okay, so why we determine the earth pressures is, as I have told you, or we have discussed, that retaining structures and foundation both we require to find that earth pressure, and that is how if I would say the retaining structures and foundations are connected, surely more applications of earth pressures in excavated cuts, tunnels, and all other say infrastructures are also there. So when I slowly and gradually move to the analysis, that what we want to discuss today is the seismic response of retaining structure, which is a very important problem, as this needs to be dealt with while say in case of seismic acceleration, the whole soil structure interaction problem is very important. And all why it is important is, it is important just because you have already a complex problem in the static itself, and then you have the seismic earth pressures which depends on the soil as a backfill, soil beneath the wall, inertial forces of the wall itself. So backfill and wall both say get to get into that, and we have also the input motion, okay, from the earthquake, or you can say the seismic force. Okay, so to get into analysis, we may have different methods, okay, which is say force equilibrium, or you can say the displacement methods. In the force equilibrium also you have various methods, including what is the majorly used is pseudostatic analysis in the practice, or you can say in most of the research work. Now, if you see in the current practices, also pseudodynamic method or pseudodynamic analysis has been very, you can say, significantly used in last, you can say, last decade. for the analysis of walls as well as the foundation. So we would be majorly focusing upon the pseudostatic method today. Also, displacement based analysis is nowadays used, and the complete dynamic analysis, including exact dynamic forces, is also being used with the help of numerical studies. Okay. So considering the pseudostatic analysis, what is pseudostatic analysis? Is we are putting the dynamic force on the structure in the form of an inertial force. So basically we are converting the force in the form of a static force or static inertial force, which is comparable, or you can say which is equivalent to the dynamic force. And this method, if we see even our IS code, IS 1893, is also adopting this for the analysis. That is, it is connecting the coefficient of say seismic acceleration AH. Okay. So similarly, this equilibrium method, force equilibrium method using pseudostatic analysis is taken, where the accelerations, seismic accelerations, are expressed in the form of vertical and horizontal seismic coefficient. Okay. Now, how this coefficient work is basically the seismic force is basically given as say or KH, which has been nominated or designated into W. So whatever is the weight into the acceleration, that is given as the force. Okay, by you can say the Newton's law of motion. Okay, and in this direction, the first work has been done by two researchers. One is Okabe, and another is the Mononobe and Matsuo, and they have developed the first method to find this pseudostatic analysis or determination of earth pressure through pseudostatic analysis. In this method, basically they have taken Coulomb's analysis, and they have extended the same by taking the coefficients in horizontal and vertical of seismic accelerations in both the directions. Okay, and that is called as Mononobe Okabe method. And if we see, still we are using this method itself for most of the analysis, and IS 1893 also adopt Mononobe Okabe method for seismic analysis of the retaining structures. Okay. Now, what is the seismic analysis that has been given by Mononobe Okabe? Is they have simply given PA dynamic is equal to half gamma h square into CA for the weight component. Surely, as we know, when we talk about retaining structures, we go with the weight part, surcharge part, and cohesion part. Okay, so if I go to the static case, we also get the same equation, that is PA is equal to half gamma h square into Ka, where Ka is again coefficient of earth pressure. Okay, now here the vector has been called as Ca, and this Ca is nothing but the coefficient of earth pressure again. Okay, in the seismic case. Okay, and you have some change in the equation of the similar. If I would go to the Coulomb's expression, okay, what you have as a new factors in this is the AV, which is the coefficient of seismic acceleration in vertical direction, and lambda. Lambda is nothing but tan inverse of AH upon 1 plus or minus AV. Okay, so what you have is basically it is the angle. If I say the weight, and then the vertical motion would have say W into 1 plus minus AV, and AH into W will be horizontal motion. So the force has the angle, equivalent force would be having angle delta, and that is nothing but the particular lambda angle. Okay, so now if I would go with this equation, okay, there is one thing that is plus or minus, so which I have to take, whether I have to take plus or whether I have to take minus for my final value, because if I get this, then I will have two values of CA and finally two values of PA dynamic. Okay, so for this particular say CA, okay, we need to have higher value. Okay, now why I have to have higher value in this case is because it is the active pressure, so it is the acting force, while in the case of say dynamic earth pressure, again similar equation has been given in the form of Cp, which is coefficient of earth pressure in passive case, but for that the lesser value has been recommended because the passive force is basically the resistance to the motion. Okay, so the least resistance should be taken for the design. So what we need to do is we need to take two values of CA, whatever is the higher out of two, that should be taken, and two values of CP, and whichever is lesser out of that, that will be say given as the final CP. Okay, so this is the simple expressions, or you can say very closed form solutions given by Mononobe Okabe in this particular theory. But what is remaining when you design is what is the force say application point, or say point of application of this pressure. Okay, so what we take as of say in the static case, when I go with this type of weight force is 1/3 from the bottom. Okay, so here similarly if I go 1/3 in the static case, but dynamic I cannot say that it will be at which point. Okay, so what we do is we just take a subtraction from PA dynamic minus PA static, and as per the suggestions of Mononobe Okabe, the PA dynamic increment. Okay, normally the passive pressure will active pressure will be increasing, and that increment will be at h by 2. Okay, so what we do is we have to take two components when we take the dynamic force. Okay, so we have dynamic increment and we have the static say earth pressure. Static pressure will be taken as per h by 3 as we have normal practice from the distribution, triangular distribution, and PA gamma dynamic should be taken as h by 2. Okay, and similarly PAQ can be taken. Okay, for PAQ again the equations are given. Okay, similarly there are few studies which I have not incorporated in this particular presentation, but there are generalized studies available for cohesion also. Okay, and similar equations can be there for cohesion also. So when I have cohesive soil, when I have frictional soil, if I have C5 soil, all we can do with this particular analogy. now we come to one more very specific, or you can say very important thing, is angle of failure. Okay, so what is this angle of failure? First is, when I talk about the failure angle, is this particular triangle AEB. Okay, that soil mass has to fail. Okay, and that has been taken in the analysis. While going for the analysis, we take an assumed angle theta I. That theta I will be the failure angle for one given case, and then we take the final failure. So what will be the final failure? Theta A critical, and that has been given by Zarabi. Okay, so what we take as say pi by 4 plus pi by 2 in the static case, okay, that would be taken as of this particular equation in case of say Zarabi's analysis for active state and Ebling and Morrison for the passive state. Okay, so what we now get as an information, if I would just summarize, is this is a validation of expression. So if I get 45 minus pi by 2 and 45 plus pi by 2 in the active case and passive case respectively or not, that that has been checked here. Okay, so if I summarize the things, we have got the seismic force first, that we have taken as an equivalent say static or equivalent inertial force, that is AH. Okay, and this AH can be say multiplied with W for inertial force or any vertical force for the horizontal inertial forces, and AB for any vertical inertial forces. Okay, then what we have taken is, we have taken the again force, all the forces, and then we have analyzed to get the dynamic force, and we have taken the point of application. Okay, now this is done for completely dry backfill. Okay, now what we have to do in the case of submerged backfill or partially submerged backfill. Okay, so for that again, IS 1893 has was giving one solution for completely submerged backfill. Okay, that has been again modified, and say some suggestions were made by us for partially submerged backfill. Now, first of all, we need to remember that what will be the difference in the case of dry and submerged backfills is, we will be having say pore pressures, as well as we will be having hydrostatic pressures or sorry and the hydrodynamic pressure also in case of the seismic accelerations, or say in the case of seismic analysis. Okay, so now if I go with the say this particular analogy, okay, then as we know that dynamic component of the weight is at mid-level and surcharge is at 2/3 of the height from the base, was being taken by the Mononobe Okabe, and what we have proposed was we have proposed an analysis, how to do the analysis, and what is the distribution that has been there, and how the analysis and design can be taken for partially submerged backfill. Okay, so what we need to do is, we need to have few steps in that. What is the basic difference that has been taken is, we have to take the delta, that is the angle of friction between the wall and soil, to half of its original value. okay, for the dry backfill, okay, in the case of submergence, and the lambda, okay, lambda we have earlier taken as tan inverse of AH upon 1 plus minus AV. Now we need to take it as say gamma S, that is the saturated unit weight, okay, upon submerged unit weight, okay, that is the gamma S minus gamma W, okay, and based on that I can find lambda, and for that submerged weights and considering all of this delta and lambda, I can again add up Monod-Ockley equation, and based on that I can find the analysis. But again, the problem would be the distribution of the force and point of action of the force. So for that, the distribution, pressure distribution behind the wall, as we take the triangular motion, or say triangular distribution in the static case, for the static condition in the retaining wall for weight case, and rectangular distribution in the weight, say surcharge case, that was being deferred, and that was considered like this, okay, where this is just distribution for dynamic increment or decrement. So that is why you can see here, that is 3Ca minus Ka, okay, while if I go with the weight only in the static case, I would have gamma H into Ka, okay, so that is the static component, and this is dynamic increment component, and or say in the case passive case we have dynamic decrement component, okay, so that increment and decrement can be taken care from this, and based on based on water level or say water table, I can find the height. Again, when I have the water table at the base of wall, I would have the dynamic increment for weight case will be at half, and surcharge case will be at 2/3. That will be the base condition. And the similarly, whenever I have increase in the say water table, I can analyze using this particular analogy. In this case, the hydrodynamic pressures of the wall will be taken separately. Okay. Fine. So, however, there has been various research that has been there, including most of the recent research which has been taken on the pseudodynamic methods. Also, I have not incorporated pseudodynamic method for today's discussion. So next, I think we would move to the foundation analysis of foundation, or seismic analysis of foundation, considering the today's session's topic and time. So I think basic introduction. I think we all know what is the functions of foundation and why it is critical to find the bearing capacity. But in the case of seismic force, okay, we need to find seismic bearing capacity and seismic settlement. Now, what is the seismic bearing capacity? Is again the bearing capacity when I have the foundation and soil subjected to the seismic forces. Okay, and if I have the seismic forces, then I may also have more settlement in case of say seismic analysis. Okay, so that is called as seismic settlement. Okay, so there has been many vulnerable seismic areas such as Himalayan belt in India, and a few foundation failures also we have taken from various say earthquakes. for which we also have a few photographs. So I would just not right now go to the failure case studies, but we will go to the analysis part rather. That is the footing when I have the static bearing capacity, as we know and we understand. We have learned all of most of these theories when the footing is subjected to vertical load or inclined load or ascending load or resting adjacent to the slope. We have various methods available for the static case, and all of them have their own pros and cons that we already have the basic knowledge of that. Okay. So with that, I would just go to 2 to 3 say literature with which I would like to just uh, start with what is the seismic analysis and how it looks to or how it changes the analysis when I go for the foundation analysis or the bearing capacity calculations. Okay, so the earliest work which could be traced out was a few literature that I have just incorporated over here, and in 1990s, mostly all the base research have been taken. That is, first is Sarma and Isophilis, and in this again the pseudostatic approach was taken with the method of slices, and uh, this was the first study. Perhaps so they have just got the horizontal acceleration rather than getting the acceleration in both the direction, in horizontal and vertical. Triangular log spiral failure surface was taken. So this type of failure surface was taken, and in this only horizontal force was taken in both soil as well as on the foundation. Now, looking to this, what will be the change, basic change when I go with the analysis is, in the case of just vertical force, I would have uh, components which is just WA, WS, WP, and here I have the W. Okay, in the case of seismic acceleration available, I would have this horizontal motion change, and because of that, when I take this passive wedge or inertial shear, internal shear zone or active wedge, the forces at the edge of all of these wedges will be say having variation in, and because of that I would have the change in the final bearing capacity. Okay, so what they have done is they have tried to give the final results in form of NCE or N gamma E or NQE, as we normally take NC, NQ, and N gamma for the bearing capacity, and same way they have given, but in the form of ratios. Okay, so NCS, NC, NQS, and N gamma S has been the bearing capacity factors in the static case, while N gamma E, N gamma QE, and N gamma E is the bearing capacity factors for earthquake condition. So this is the table that, the graph that has been given by Isophilis and Sharma and Isophilis. Similarly, the Richards Hasan also have given the analysis for the similar type. But what was there is, you have the change that was taken was, they have also incorporated vertical acceleration. Okay, in the case of the Richards. Okay. So these are the equations given. In this, again, directly bearing capacity factors were being taken instead of the ratios for NQ and gamma and C. Okay. Then the Budu and Kearney method, which was again one step ahead in form of they have taken the mobilization, okay, in the soil, okay, so or the soil strength. So they have taken mobilization ratio by considering the analysis and how the seismic and static failure surface changes they have given the results. Okay, so what they have done is they have given again in the form of NQE by N gamma A and N gamma S NQE upon NQS. So the bearing capacity was given in form of again bearing capacity vectors in form of ratios. Okay, so in continuation to this, we have also tried to do a limit equilibrium analysis in say similar line to what Budu and Kearney has taken, but considering the rough foundation using the base model as the failure mechanism modified by Sarin from Terzaghi, and while if we go to the basic formula that is was adopted by the Budu and Kearney. Okay, so this was taken firstly that change in the modified ratio and the factor multiplying factor for different this coefficient was considered. That multiplying factor was nothing but the mobilization for various AH. Okay, so looking to this, various researchers have done this. So I've just tabulated it for the purpose of reporting over here. That various analysis was taken from different methods, including pseudostatic, pseudodynamic, and kinetic analysis. Kinematic analysis, considering vertical acceleration, horizontal acceleration, that has been covered. But if we see the most of the analysis, they do not have taken the effect of eccentricity in the vertical, in the stick condition. Okay, now what I would be starting to present is some few glimpses of the work that was being done during my research work at PhD level was the seismic analysis, bearing capacity analysis, considering the static eccentricity, okay, which was not covered in any of the earlier research. So here, if I just take this are the three factors, okay, static vertical force, horizontal force, and movement, okay, for which normally we design in the case of usual foundations, right? Now with incorporating this, okay, what I will have, I'll have also the seismic force, okay, and this seismic force would be, say, first is the vertical seismic force, which will be taken, then horizontal seismic force, okay. So in the earlier cases, what was taken is AH was taken here and AV was taken here, okay. So AV will not have any large difference, but AH, if I take it on the base of the foundation, okay, it will not be acting as the base of foundation, it will be acting at some height above the foundation at the structures level, right? So Now, if I incorporate that also, that is the dynamic eccentricity or the dynamic movement, okay, horizontal seismic force which is generating the movement at level H, then there would be a complete consideration of all the forces, and that was tried to or they attempted for this particular analysis. Okay, so what was considered is simply these three basic factors or say basic forces: horizontal static force, vertical static force, and moment. Okay, which is normally we take it as eccentricity and inclination, and on the basis of this we analyze the foundation for the static case. That is already we are doing, right? But in the case of seismic accelerations, we have two more factors and one movement that will be taken. So, if I would just sum it up all, then there will be dynamic horizontal force, dynamic vertical force, and dynamic moment. And based on that, I would have the say my force, including my eccentricity and inclination. Okay, so all of this equation or say expressions suggests various formulas for converting the forces to the equivalent force. Okay. Mm. Fine. So with that and the mobilization force that was considered earlier also in the case of Alkermes analysis, that was characterized and that was developed in the analysis. So I think that would basically uh, cover most of the assumption, including one more thing that we have tried to incorporate in the analysis is the width reduction factor. Now, what is this width reduction factor? Is when I have eccentric force or say eccentricity in the my analysis or in my foundation, what happens is when the eccentricity goes out of the kernel, okay, that is E by B is more than 0.16, what is happening is my uh, width would be effectively decreasing, right? So that effective width would be reduced, and that was being taken like say for example the BC is the original width, then I would take AB as the effective width, and based on that, we would be taking the eccentricity calculations. So, the width reduction is also considered, the mobilization factor was also considered, and seismic acceleration and effect of horizontal seismic acceleration on structures was also considered while doing the analysis, and based on which the failure surface was developed for the analysis, which was in turn give us the final bearing capacity factors. Okay, so these are all basic geometry and basic analysis that was considered, and again the NC, NQ, and gamma general bearing capacity factor, also generalized bearing capacity uh, say equation was again used for the same. Okay. And conducting analysis for different factors that has been considered. Okay, alpha 1, alpha 2, and M was taken. That I will just say tell you, or we will just discuss the procedure for that. But what was you can say challenge over here was the alpha 1 and alpha 2 for developing that failure surface. Okay, because we have changed AB width from BC, so we could get some of the theoretical analysis, but alpha 1 and alpha 2 and the mobilization factor that was taken. So first of all, what is alpha 1 and alpha 2 is the angle which is developed at the central wedge or wedge 1 over here in this particular biliar surface was taken, and I think based on which what we have done is we have set a procedure to get first the values of various factors, input factors, assuming a value of m and alpha 1, we would be considering alpha 2 by satisfying moment equilibrium, then satisfying horizontal equilibrium and get alpha 1, and satisfying the vertical equilibrium or say sigma v is equal to 0, we will get the m. So we have three knowns, alpha 1, alpha 2 and m, and three equations, so that can be satisfied by having alpha 1 the various inputs like phi, is, es, ah and h. Okay. In this, we have considered v, that is the vertical acceleration, as 2/3 of ah as been suggested by IS 1893 2002. So with that we have considered, or we have taken static analysis first, considering ah is equal to 0, which was in agreement to Saran's work, and we also tried to find regression analysis for n gamma, because n gamma is always a complicated expression, and that is why we have just regraded to get a more simplified expression for n gamma as n star gamma as. Okay, and then subsequently we have done the analysis, where again we have represented it in a reduction factor, or the seismic reduction factor. The seismic reduction factor is nothing but, as we have seen in the Earl-Kearney's analysis, that is n gamma e upon n gamma s, that is the bearing capacity factor corresponding to seismic analysis to the static analysis has been taken. So this is one of the representative table just I have put for the values. So if you see for ah is equal to 0, e by b 0, h is equal h is nothing but the height. Okay, so as the ah is 0, height would not have any effect. So their seismic bearing capacity factor ratio, or say seismic reduction factor, is 1, so you don't have any reduction. While if I move further, there is a quite higher reduction in the case of movements. Okay, and even if I would just take this particular case, when I have higher acceleration, okay, and when I take h is more, then I would have the more quite higher decrease in the bearing capacity. Okay, so while incorporating this for design, what I have to just take is, I have to take the basic parameters, input parameters, which is known to us, like for example phi, is is basically inclination in the static force, eccentricity in static condition, ah, that is the seismic acceleration. I think that can be developed, or so that can be found out from the codal provision in the IS 1893 2016 in a case of Indian standards, and h, that is the height of the seismic acceleration, that can also be taken with the help of modern analysis that, suggested by IS 1893. Okay, based on that, I have to find suitable width, as we already do it in designs. Okay, obtaining the SRF from this particular table for the given condition. Okay, so various set of tables has been given in the report, thesis report, what was been given. So here I have just put one table for representation, and as I go with this, I can find the whole ultimate bearing capacity. And similarly, what we do for the static condition, it has been simplified in the very simple with the design tables that has been developed for all the cases. So here we have just incorporated one particular say example, and we tried to get it with the comparison. Okay, so if I just go with the comparison with corresponding seismic bearing capacity, okay, we can see that it is quite obvious to have the lower bound. Okay, so if even I would take say, so this is basically QUE upon QUS. So bearing capacity in earthquake condition to bearing capacity in static condition, and that is what we want finally as the result. Okay, so fine. I think I would. So that is what is the static capacity, bearing capacity for flat grounds. Similarly, we have developed for also the sloping ground, where the slope, angle of slope was also being considered, and similar analysis was taken for the seismic bearing capacity for foundations on sloping ground. Okay, fine. With that, I think I would just go to for few of the things that I was just thinking about, or I was in the line of doing, was a complete analysis was done for the seismic case only for bearing capacity, but seismic settlement has not been worked out. Uh, so seismic bearing capacity and seismic settlement both should be worked out, computed, uh, based on which only we can develop the complete design. A few experimental study, very few experimental study, I would say, has been developed considering factual field conditions. Simulated experiment should be done and should be directly relatable to this theories, uh, whichever we have discussed in the session, and new materials maybe also expedite. That is what we would, I think, try to pursue in future. And similarly, I think the codal provisions should be also uh, taken and reaffirmed regularly. I think now we have got this IS codes are also reaffirmed. It's for IS 1893 at least. So thank you very much. Uh, with that, I would just share the key references which we have got. I think you can see this particular book chapter that was there in the advances in earthquake engineering for the seismic analysis and design of retaining walls, where we have also covered with pseudodynamic methods as well as dynamic methods, and I think the PhD thesis. Again, I have also got many of the bibliography over here. Thank you for the patient hearing. Thank you very much, sir. I hope I have completed in the time that I have been given.
Okay. Thank you, Dr. Hasan Rangwala. Before summarizing the lecture by Dr. Shruti Shukla, I am thankful to Professor S.R. Gandhi, Professor Murli Krishna, Professor V.A. Sawant, Dr. Raghuveer Rao, Sanjay Verma, Dr. Vikas Patil, Ashish Mehta, Dr. Atmakurti and Srinivas for your presence here in this lecture. If you have any questions you may ask directly to Dr. Hasan Rangwala. I request Professor S.R. Gandhi to say a few words on this occasion. We have arranged this lecture on the 9th date anniversary of Professor M.D. Desai. Sir, you unmute yourself.
Thank you, Professor Solanki, and very good morning to all of the participants. I am thankful to Dr. Professor Rangwala for the very interesting talk covering the seismic aspects of bearing capacity, the loss of contact, and in fact, this is a subject which is not much covered in the code, particularly when you have a circular foundation like a chimney or and when you have a loss of contact due to the high moment coming due to earthquake, how do you get the contact stresses is really a challenge. And I am sure Professor Rangwala's work carried out will help in this direction. I'm sure that IGS will be organizing such events regularly, and we look forward to participate in the same. Thank you again, Professor Solanki, for this opportunity.
Thank you, sir. I request Dr. Shruti Shukla to summarize the lecture and conclude the session.
Thank you, Solanki sir, for giving me this opportunity. On behalf of coordinators, myself, Dr. Shruti Shukla, Dr. Shailendra Kumar sir, and Dr. C.H. Solanki sir, I thank all the participants who are present over here. Special thanks to experienced faculties, which Solanki sir have already mentioned, and Dr. S.R. Gandhi sir for presenting over here and encourage the student chapter particularly to organize such events. Your auspicious presence is highly acknowledged, sir. And special thanks to Rangwala sir to spare his valuable time to deliver his lecture on this interesting topic of seismic analysis of bearing capacity and retaining wall, because it is very uncommon topic which is studied over in the area of soil dynamics, and it is highly recommended for the research students who are working in the area of dynamics to work on this topic, because it is very untouched topic so far. A special thanks to Dr. Rangwala sir for sparing his valuable knowledge to us, and I thank you once again, one and all, to be present over here. With this, I'm concluding the session. Thank you, sir.
Okay. Dr. Raghuira, would you like to say anything here?
Yeah, it's a very interesting talk. Actually, I learned something more about this, though I've been teaching this subject for some time, but I learned a little more about this, that increment and decrement thing. Thank you very much, Dr. Rangwala.
Okay. Professor V.S. Sawant, are you here? Dr. Sawant? Okay, he might have left. Thank you, Dr. Rangwala, for your excellent presentation. Thank you all. Thank you
very much for giving me the opportunity, and thank you, I think, for Gandhi sir, Raghuvi sir, Shruti ma'am, all. Thank you very much, sir.
Okay, thank you. So we conclude the session and this lecture. Thank Nazim Ali.
Yes, sir.
You can stop the presentation and links.
Okay. Thank you all for joining.
Okay, thank you.